Good morning, ladies and gentlemen. Today we are learning about the last piece that goes with the mole, and that is molar volume. Before we get into molar volume, there's this thing we need to discuss, and that is standard temperature and pressure. So when it comes to moles and volume, when it comes to volumes of gases in general, now you need to take more things into consideration because temperature and pressure can affect how much space gases take up. And I'll give you an example of that with a demo. So here you have a gentleman inflating a balloon. Well, the balloon has nothing but air in it. He puts the balloon then inside a bath of liquid nitrogen. If you did not know this, liquid nitrogen is very cold. Okay, so as the balloon gets colder, notice that it starts to shrink. Okay, the air isn't becoming liquid. It is very difficult to liquefy air, pure air. But notice that as the balloon gets colder, it starts to shrink. Okay, the gas starts to condense. And then when he removes it and pulls it back out, as it warms up, notice that it starts to expand again. Okay. So the point of that was just to tell you that temperature does affect the volume of gases. So in order for us to accurately compare things, we need to have a standard. So when we talk about volumes of gases, we are going to be talking about gases at a specific temperature and at a specific pressure. And that is known as STP. So S stands for standard, T stands for temperature, and P stands for pressure. So that's what STP stands for. The standard temperature is considered to be 0 degrees Celsius, okay, or 273 Kelvin. Kelvin is another unit of temperature. And the standard pressure is considered to be 1 atmosphere. Okay, 1 atmosphere is normal pressure. Okay, so like right now, us just being here on the ground, we feel 1 atmosphere of pressure. That is the pressure of the world. Okay, if you were in the mountains, however, like if you were in Colorado and you were up on the mountains, the pressure does get lower as you go higher. But we assume that for these purposes, atmosphere, the pressure around this is 1 atmosphere. Okay. So for a mole, when we're talking about 1 mole of gas, here's the new bit. At STP, so that means at 0 degrees Celsius and at 1 atmosphere, 1 mole of a gas would take up exactly 22.4 liters. Okay. If I don't know if you guys remember the mole box, but that box I had in the room that's representative of a mole, that is how much space 1 mole would take up if it was a gas and at STP. Okay. So that's the new bit of information. It doesn't matter what the gas is. It doesn't matter if it's steam. It doesn't matter if it's hydrogen gas. It doesn't matter if it's nitrogen gas. It doesn't matter if it's helium gas. The gas does not matter. If it is at 0 degrees Celsius and 1 atmosphere, and you have 1 mole of it, it's going to take up 22.4 liters of space. Period. Okay? Does not matter. So comparing it back to the other previous, the moles and volume and mass and all, and the particles. There we go. 1 mole of gas is Avogadro's number of particles, and those particles will take up 22.4 liters of space. Okay. It does not depend on the type of gas. It is true for all of them. It doesn't matter which one you have. Okay. And this is basically this entire section. This is the important bit of this section. Okay. From there, it's just what you've done the last 2 days. There's going to be a formula that you use to go between moles and volume. And then we're going to look at a little triangle that connects all three of them. Okay? Okay. So this question is one I want to go through a little slow just because it'll highlight all the potential misconceptions you may have. Okay? Because I said it doesn't matter which gas you have, and that is true. No matter what gas you have, it's going to occupy the same space if it's under the same conditions. Okay? But let's answer these questions real quick. So we are comparing hydrogen gas to carbon dioxide. Okay? We have 2 moles of each gas. So we have the exact same number of particles of each molecule. Okay? And it's saying what must be true if they are at the same temperature and at the same pressure. A. Each sample will have the same density. This is not true. This is wrong. What is density? Density is mass divided by volume. Okay? Density is mass divided by volume. Both gases will have the same volume if they're at the same temperature and pressure. However, they will not have the same mass. As we are well aware, different elements have different atomic masses, okay? They have different masses. So while they have the same volume, they will not have the same mass, which means they will not have the same density, okay? So that's why A is wrong. Okay, A is wrong. They will not have the same density. B, the same number of atoms will be present in each sample. This one you have to be careful with because these are not individual atoms. These are molecules. They're molecules because they're made up of more than one atom. Okay? So in one hydrogen molecule, there are 2 atoms. You have 2 H's. In one carbon dioxide molecule, you have 3 atoms. You have 1 carbon and 2 oxygen. So there are 2 atoms in this one, and there are 3 atoms in this one. Okay. Now you'll have the same number of particles. Remember, particles is used to reference everything. Okay. When I say particle, I could be talking about an atom or I could be talking about a molecule. Particle covers both. So they'll have the same number of particles. There will be the same number of molecules of both. But because they're made up of a different number of atoms, if you're looking at specifically atoms, they won't have the same number. Okay. So if you wanted to find out exactly the number of atoms, you would take for hydrogen, you would take Avogadro's number and you would double it. For this one, you would take Avogadro's number and triple it. Okay? So it's not B. Each sample will have the same mass. That is not true. We talked about that one already. They'll have the same volume, but they will not have the same mass because different elements have different masses. Okay? Each sample will occupy the exact same volume. This is true. Okay? This is true. If they're at the same temperature and at the same pressure, they will have the same volume. Okay, so the answer here is D. Okay, so hopefully you understand why A, B, and C are wrong. Okay, but I wanted to highlight that because this covers all those things. Okay, so here's the new formula for today. If you want to go from moles to volume, this is the equation you use. Okay, VM, VM is always, this is the 22.4. Okay, always, this is always 22.4. That's what VM is. Just how Na is Avogadro's number, and then the big M is molar mass. Okay, so VM is 22.4. So what this is saying is that if you know the volume, you can divide it by the volume at STP. I'm sorry about that. You can divide that by the volume at STP and figure out how many moles of something you have. Okay, that's what this equation is for. And now let's practice using it. Let's apply it. Scroll down, please. No, how many moles are there in 44.8 liters at STP? You're going to see this a lot, okay? They're going to specifically tell you that it's at STP more often than not, just because, as we learned, temperature and pressure does affect your gases, okay? If we're not at STP, technically, we can't use this, okay? If we were not at STP, VM would not be 22.4. So that's why they have to reference that. So how many moles are there in 44.8 liters of this fluorine gas? So N is moles, V is volume, Vm is the 22.4. We are looking for moles, so we will leave the equation as is. So N is equal to, what is our V? Our V is 44.8. And then we're going to be dividing that by Vm, which is 22.4. And if you put that into your calculator, you are going to get 2. Okay. So this is the exact same stuff you've been doing already. We're now just doing it with volume instead. How many moles of an atom? So how many moles of atoms are there in 22.4 liters of xenon? Okay, so now this question's a little different. So this question would normally take 2 steps, okay? And I'll show you what I mean. Let's get the moles first. Okay. So we have 22.4 liters of this gas. So N equals V is going to be 22.4. That's what it's telling us, is we have 22.4 of it. And then we divide that by 22.4. So then we have 1 mole. Okay, this is equal to, this is 1. We have 1 single mole of xenon. But they're specifically asking how many moles of atoms. Okay. Now, because we're talking about xenon, the answer is still going to be 1. And the answer is going to be 1 because xenon is not one of those things that needs to live in pairs. You can have a xenon by itself. So elemental xenon is just 1 Xe, okay? So in one xenon particle, there's only 1 atom. So we would have to multiply the moles of xenon by how many atoms are in 1 xenon. So it would be 1 times 1, which would still be 1. However, if instead of xenon, it asked for hydrogen or oxygen, you would have to double this number. Because in 1 oxygen molecule or in 1 hydrogen molecule, there are technically 2 atoms, okay? So just be careful with that wording. The answer is still 1, but that's only because in 1 xenon particle, there's only 1 atom. Okay? That's one of those questions that they can get you. They can get you. Okay? So I think that's enough of these examples because they're all going to ask us the same thing. And I think you guys have gotten familiar with these. Let's do one where we're going from moles to volume. Okay? So this is the moles to volume. We've done volume to moles. Now we're doing moles to volume. So we want to know, what is the volume of 4 moles of nitrogen if we're at STP? So we're looking for V now. We're looking for V. We need to rearrange the equation. If you do that, you get that V is equal to N times Vm. You get that by multiplying the Vm over, okay? And then you get rid of it on this side. V is now equal to, we know the number of moles. We have 4. And then times Vm. Vm is 22.4. Put that into your calculator and you get, what is this? This is going to be 88. This is 1.6. 89.6 is what you would get. Okay. Here they talk about a real world application. Airbags. Airbags are inflated with a gas. How much gas do we need to prepare in advance for it? Well, that depends on how hard we want the bag to be upon inflation. Okay, so these molar volume calculations, this is a scenario where they would be used. Okay, preparing an airbag and making it safe. You don't want to put too much gas that it becomes rock hard, because then you defeat the purpose of the airbag, which is to protect you and cushion you. And you don't want to put too little gas, because then it won't protect you at all, and your head is going to hit the steering wheel anyway, which what the airbag is trying to stop you from doing. Okay, so that's molar volume. Okay, and if we combine everything we've discussed over these last 3 days, We have moles to particles. That's this one, okay? N is number of particles. Na is Avogadro's number. So this is the one we use if we're talking about particles. This is the one we're using if we're talking about the mass, where little m is mass and big M is molar mass, okay? And then this is the new one we learned about today. This is for volume, okay? So this is the triangle. Okay, this is the triangle. Where is it? Okay, the road map. So in the middle you have moles. If you know how many moles of something you have, you can figure out its mass. You can figure out its particles, and you can figure out its volume. Okay. And now we can also do two-step equations. Okay. I can have you start anywhere on this triangle. Let's say I start you here. I can have you. Let me clear this. It's starting to get a little crazy. Okay, let's I can start you here at volume, and from volume, I can ask you how many grams of something do you have? Grams is mass, which means I'm asking you to go from volume to mass. To do that, it's two steps. First, you need to go from volume back to moles, and then from moles to mass. Okay? So now we can start doing multi-step problems now that we learned the three sides of the triangle. Okay? So that's what's going to start happening. This is what you've been doing the last few days. You just use the formulas to figure out which section they're asking you. Okay? And I think that's it. The rest of these are just examples. I'll do one example where it's a two-step. After that, it's a new section. The rest of these are just practice. Okay? So let me find one where it's a two-step. I believe this is the two-step. Yeah, this is a two-step. So we want to find, this one is asking us to go from particles, okay, because it's telling us how many specific atoms we have. We want to go from particles back to volume of hydrogen. Okay. All right. Cool. Cool. So first things first, we need to figure out how many moles of hydrogen we have if you want to figure out the volume. So the one we're using first is this one. This is the first equation we're using. We need to find out how many moles we have. So moles is equal to N, which is 6.0. Problem says times 10 to the 23. Now, for the sake of making things cleaner, I'm going to round Avogadro's number down to 6 as well. Because this is saying 6.0, this is saying 6.02. It's going to be pretty close to 1. Okay, so I'm just going to round it to 1 just to make life simpler. And then you end up getting 1. Okay, so this is how many moles we have. This is how many moles of atoms we have. Okay. And notice the question, they're referring to atoms. Okay, they're referring to atoms. This is the same as the question before where I told you need to be careful when they say atoms. How many atoms? Where's the one we just did? Here. The one we just did here was xenon. Okay, how many moles of atoms? It's the same situation here. So how many atoms are in one hydrogen gas molecule? Okay. In one hydrogen gas molecule, it's HH2, right? Hydrogen is H2. So we have this many atoms of hydrogen. So we have 1 mole of these atoms, but that does not tell us how many moles of hydrogen we have. We need to divide this number by 2 since one hydrogen molecule needs 2 atoms. So instead of 1 mole of hydrogen gas, we now have half a mole. We have 0.5 moles of H2. Okay. This is how many moles of hydrogen gas we have. Okay. And now that we know how many moles of the hydrogen gas we have, now we can find the volume. Okay. V would then be equal to our 0.5 times 22.4, which would then give us 11.2. Okay. So just know if they're referring to atoms, you need to pay attention a little more and just make sure that you're covering your bases. All right. But that's it for today. I'll do one example from the worksheet because I think you guys are getting the hang of it, and I will call it. And where are we on time? This has been the shortest one so far. Oh, 20 minutes. All right. Not as short as I thought. My apologies. So I'll just do one of these. And yeah, you guys are getting the hang of it. All right. 24. How many moles are in 2,000 liters of helium at STP? So we want to find N. We are looking for moles. So we're looking for N. We're working with volume. So N in this case would just be 2,000 divided by 22.4. Okay, put that into your calculator. You will get your final answer. All right. Thank you guys for your time. Wish you all the best. Again, as always, if you have any questions, need any clarification, please feel free to reach out. Take care and enjoy the rest of your day.